So this is just an introduction to the angular momentum of particles and rigid bodies. But before we do that, I want to make sure that we get to review torque, okay, and the direction for torque. Now, there are several things that I want to make sure we know, okay, and it's how to use the right-hand rule to determine the vector directions for four different things. For the angular velocity, okay, for the angular velocity, the angular acceleration, the torque, and the angular momentum. They're all based off the right-hand rule exactly like it shows in that picture. All right? Now, as far as we're concerned, that is actually, I want to review torque, and I want to review the old way that we talked about torque and a new way that we're going to use. And it's essentially the same equation. All right? Now, you could actually find the torque for a particle about a particular location, and it doesn't necessarily need to be a rigid body. Okay? And we'll talk about the implications of that later. But right now, this is just a review of calculating the torque and how we, our method for it. All right? So remember, when we wanted to calculate the torque, what were some of the, what did we want to do? What was the method that I showed you? What do we want to do first? Does anyone remember? You guys remember the line of action and all of that? Has that been that long ago? Okay. So remember, I told you guys that we should draw a line of action. Okay. So the line of action is drawn along the force. Okay. So I've got that force, which is represented by that red line. And I would find the lever arm. Okay. So we said that the lever arm would be, let me choose a particular color here. The lever arm would be the distance from the axis of rotation. So in this case, the axis of rotation is right there to the closest point on the lever arm. Okay. So in this case, my lever arm's length is how much? Is 3 meters. Okay. So I plug that into my equation of 3 meters. All right. The force is, excuse me, the force is 2 newtons, so it's simply 2 times 3, and that gives us a torque of 6 Newton meters. All right, you guys remember that? That's sort of the way I gave you, the kind of the old way I gave you of solving that. All right. All right. Now, what I want you guys to also see is this. Now, this equation, right? This equation for the torque is the vector cross product notation for the calculation of torque. It says you take the r vector, okay, which could be in this case it would be 3i plus 4j. Okay, it would be 3i plus 4j, and take the cross product of the force vector, which would be 2j, and you would have to do a vector cross product calculation. Now, we're not going to do that. What we will do is this. We're just going to take the two magnitudes and plug it into this equation here. Okay? So this equation essentially becomes this equation. If we take the magnitude of the r vector, okay, in this case, we know that its length is 5 meters. We take the magnitude of the force, okay, and we know it's 2 newtons, and we take the sine of the angle between them. All right? So, that is the other way. It's essentially the same way, but that's another way we can solve this torque problem. So I take the magnitude of the position vector, the magnitude of the force vector, and the sine of the angle between them, and that will give me the torque. Okay. Now, if I asked you, what is the vector direction of the torque based off the right-hand rule, it would be what? It would be out of the page towards us. So the vector direction would be out of the page toward us. Okay. All right. So again, that's just a review of calculating out torques. All right, and you're going to see how this applies to angular momentum here in a minute. Okay. All right. So all you need to do for those guys writing notes, all that really matters is this equation here. Okay, as long as you get that down, you're good. The fact that this equation here becomes for us that equation. All right. So remember, this is one of your equations on your equation sheet, correct? All right. Yes.
I'm still confused. I know what's calculated, but I don't get 6 multiplied by 5.
Okay. So apparently I got the wrong one there. Thank you for pointing that out. So this angle, because this would have been 53, that should be 37. Sorry. So 37 degrees. 37 degrees. I fixed that on my handwritten notes. Apparently I didn't fix that here. 37 degrees.
R is the angle between your letter R. Nope.
R is the angle between, yeah. Okay, so theta is this angle. If I extend my R vector and compare it to my force vector, it would be that angle. Okay. All right. Now, so now we're going to study angular momentum. Okay. I think this kind of goes back to your guys' notes packets. Okay. So it says angular momentum is a quantity that tells us how hard it is to change the rotational motion of a particular spinning body. Okay. Objects with lots of angular momentum are hard to stop spinning or to turn. Okay. And objects with lots of angular momentum have great orientational stability. So, for example, you take a top, right? A top that's spinning, a typhoon or a hurricane, something that's spinning like that. I mean, as soon as you get it spinning, a tornado, right? Well, tornado is a little different because it's more, there's a lot of other factors. It's a pretty chaotic event. Those all refer or are good examples of angular momentum. Okay? All right. So the angular momentum for just a particle. So you need to make sure we keep these straight. All right. I think one of the problems we had back when we were studying rotational kinetic energy, or not rotational kinetic energy. I think it was the moment of inertia. Some people were getting the moment of inertia of a particle around a certain point, which is mr squared, confused with the rotational inertia of a rigid body, which depends upon the geometry of the rigid body. Let's make sure we don't do that for angular momentum, okay? There are two equations. One equation is the equation for a single particle for the angular momentum, okay? And it is this equation here, okay? Notice it's also a vector cross product equation, all right? It says that L, and I know it's weird, okay? Everyone thinks it's weird that L is the angular momentum symbol, but L is the angular momentum. It is equal to the vector cross product of the position vector versus the momentum vector. Yes?
Is there a difference between a cross product and just a product?
Okay. Yes. All right. And that's why that's the math that I don't think we really need to get into. And based off what I showed you, we're going to do the same thing here. We're going to do R times P times the sine of the angle between them. Okay? All right. So the L is angular momentum for the single particle. Okay. R is the distance from the particle to the point of rotation. And P is the linear momentum. Okay. What's the equation for the linear momentum? Mass times velocity. Okay. So we all have that, right? You guys have all that okay. All right. So good. Okay. So to determine the angular momentum for the revolution of the moon, I want to make sure I get the rest of my notes here because I don't want to do like I did on the other thing where I wrote one thing down and put in a different, something else. Okay. We'll just do the part A here. Okay. We're going to treat in this particular problem, we're going to treat the Earth as just a huge point particle, right? And in that equation, we have that L is equal to R, and we're going to cross it times P, okay? So the other way we could write this is that it's R, since momentum on its own is mass times velocity, okay? So I can write that as the momentum is the mass times the velocity, okay? And then I'm going to put the sine of theta, okay? All right. And in this case, the sine of theta is going to equal 1, right? Because my, it's essentially the sine of 90, right? Is the sine of 90 equal to 1? Or is it sine of 0? Which one is it? The sine of 90 is equal to 1. Thank you. All right. So, because if I've got the Earth out here, okay, I've got the Earth out here, and I got the sun, okay, my position vector is going to point out like this, R, okay, my momentum vector is going to point in a direction perpendicular to that, right, in all situations. So this angle is always going to be 90 degrees, okay. So in this particular setup, I literally just have R times m times v, okay? And for the velocity of an object going around in the circle, you guys remember that? What's the velocity of an object going around in a circle? Good, 2 pi r. Some of you guys had it, okay, over the period. Okay, so I can plug this value in for v. Okay, so I would end up with essentially 2 pi m, that's supposed to be a 2 pi m r squared over t. I better fix that. Otherwise people look at that and be asking what in the world that is. So 2 pi m r squared over t. Okay, so I'll just give you, these are all values you could find. I'll just give you the answer. It's like really huge. It's like 2.66 times 10 to the 40th. And the units are kilogram meters per second. Okay. All right. Now, I want to make sure we get, okay, so the moon, so we're only going to do A. All right, so that's how we apply that equation. All right, now, this is the example, this is the reason why I brought up that torque equation again. All right, I want to make sure that we can solve this cross product using that method that I showed you earlier. Okay, so it says, determine the angular momentum for the 2 kilogram particle shown. We'll just do part A on this. Okay. So again, we've got our equation for the angular momentum is equal to the cross product of the r vector times the momentum vector. Okay. The way this is written out, it should be written out as with arrows above this. And I had my calculus teacher at Cal Poly always drew half of an arrow, and I just got used to drawing it that way. So I can figure this out, okay, because remember we said that for the cross product, if I just multiply the two magnitudes and multiply it times the sine of theta, I should be okay. All right, so it would be essentially that, okay. Then I get R, and the momentum is just the mass times the velocity as well. Okay, times the sine of the angle. Okay. All right, so as I calculate this out, okay, I get, let me make sure I have my picture here. So here's the velocity of it. It's moving in this direction. I've got this other, remember my other vector goes out like this. Okay. So if that vector goes out like that and I go and I extend it, this is what Justin was asking earlier, what that angle was. Essentially, this would be the angle theta there. Okay? But as you guys notice, that angle theta right there is the same as what other angle? Where? Good, right there. That angle there. And this just goes to 0, -2, and this is positive 2 right here, I should say. Oops. This is positive 2 right there. Okay, at that point. So what should that angle be then? Should be 45 degrees. Okay? So if I take my values, let me rewrite them over here. I take R, okay, R, which is going to be what value if I've got this as 2 and that is 2? How am I going to calculate out R? Okay, 2 times root 2. Okay, so R is going to be 2 root 2. Okay. Does that come out to 2.83?
It doesn't matter, it cancels out.
Oh, because of the sign?
Yeah.
Okay. And then I take the mass. Okay. The mass of the object is 2 kilograms. Its velocity, we said, was 3 meters per second. And the sine of 45 is what? 0.707? Is that what you're saying when it's going to cancel? Is it root 2? Okay. So that if that becomes root 2, I just get basically it's root 2 over 2. Okay. So I get 2 root 2. Let me just put these all in here. Times essentially 6, right? Times the square root of 2 over 2. This 2 cancels with that 2. And the root 2 times the root 2 becomes just 2. So 2 times 6 becomes 12. Okay? And we need to make sure we include the units of kilogram meters per second. Okay? Or you can just use your calculator. All right? Now, you guys will also notice that we could have used that lever arm thing too and found that this distance here was 2. And so we just used 2 times 3 times 2 to give us 12 kilograms. Yeah. Okay.
I guess I'm confused with where that particle goes. So it's rotating about the.
Yeah. Okay. So yeah, you know what? I should have just briefly talked about this. We can even though for a particle. Okay. So that's our equation. All right. Now for a solid object. Okay. So we'll just do the angular momentum of the solid object. Yes.
Okay, in the beginning we talked about that path.
Yeah.
Gives you an
just
idea.
yeah. Just for at that point though.
Yeah.
Yeah. Okay. You know, I'll try to come up. I got a good example for discussing the angular momentum for a straight object. Okay. All right. Now, so for a solid object. Remember, it's linear. To calculate linear momentum, we literally just take the mass times velocity of that object. Okay? Now, what we're going to do with angular momentum is we're going to replace momentum with angular momentum, and then we're going to replace the mass with a rotational inertia. So I think this might go on your, what is that thing called? The analog sheet. Okay, if you already haven't plugged stuff in. And we'll replace velocity with angular velocity. And that'll be our angular momentum equation. Okay? So make sure you get these straight. This is the equation for the angular momentum of a rigid body or a solid object. The previous equation we used was the angular momentum for a point particle. All right? And sometimes you may have to add them. All right? Okay. So where L is angular momentum and I is a rotational inertia. So all you really need to get from this is just this equation there, the angular momentum. Okay? Now, and that should be like omega, right? That should be omega, the angular velocity. Okay, so I'm just going to set this up. This is going to be the last thing we do, because you'll see that these are actually pretty easy. It says to set up the calculation of the angular momentum for the rotation of the Earth on its axis. Now again, we're treating the Earth now as a solid object instead of a point particle. Okay, like we did earlier. Okay, so make sure you get the two equations separate. Oops, I didn't mean for that to go off. So remember, for a point particle, it's L is equal to R cross P. Right, for an object, a solid object, it's I omega. Okay? In this case, because we're going to treat the Earth as a solid object, we're going to use that equation. All right? Now, what kind of geometry, what kind of object should we treat the Earth as? Even though it's really not like this. It's going to, what? No, in this case, we're going to treat it as a sphere, okay? And so what's the rotational inertia of that? Okay. Remember that? It was a 2/5 one. Okay? So 2/5 mr squared. Okay? And we're going to multiply that times omega. So let's figure out how would we calculate omega. Omega would be equal to, if we go around once, that would be how many radians to go around once? 2 pi. Okay, even though it's it's still the Earth, it's 2 pi because it's going around in a circle. We need to figure out how many seconds that is. So for the Earth to go around its axis, we would need the period. So that would be 24 hours times how many seconds? Yeah, there's 60 seconds and 60 minutes, so 3,600 seconds. Okay, so I would take this value and I would just plug it into here. Okay, I'm just setting this up. We're not actually going to calculate it. So 2 pi over 24, that should be 24, times 3,600 seconds. Okay, so you would need the mass of the Earth and the radius of the Earth. Okay? All right. So that's all we're going to go over as far as this stuff is concerned. The only other